In this lesson, we'll explore solubility, which is how substances dissolve and how to interpret solubility curves. Let's start with what a solution is. A solution is a homogeneous mixture, meaning it looks the same throughout. The solute is a substance that is being dissolved, like salt or sugar typically, and the solvent is what does the dissolving, often water. So in salt water, salt is the solute and water is the solvent. Solution forms depends on the physical state of the solute and the solvent. This image shows a container initially containing two gases separated by a barrier. When the barrier is removed, the random motion of the gas particles causes the two different types of gases to become uniformly mixed in the container. If you are talking about two solids, they can also mix together. Typically, what people will do, though, is they will melt them so they're in the liquid state because that makes it much easier to get the two different types of metals to mix, or two different types of particles in the solids to mix. However, if you have them in contact for a really, really long time, the motion about their fixed position will eventually cause them to exchange positions with each other, and you end up with a very, very thin layer where the two substances are mixed at the interface between the two initial substances. If the solvent is a liquid, and this is more typically what we think of when we think of preparing a solution, the solvent molecules, the way they can dissolve the solid is they will adsorb down onto the surface and then surround the different ions and pull them off into solution. So this media clip is from the Canadian Museum of Nature, and it illustrates sodium chloride dissolution in water. So here's a water molecule. And the yellow and pink structure is a sodium chloride crystal. So the pink ions are going to be the chloride ions, and the smaller yellow ions are going to be the sodium ions. Remember that water is a very polar molecule. It has a permanent dipole where the hydrogen ions have a permanent positive charge and the oxygen atom has a permanent negative charge. These charges are attracted to the opposite charges in the sodium chloride matrix. They adsorb down onto the surface, form a hydration sphere, and carry off the ion into solution. If we're talking about a cation, then the negative oxygen is going to form the close contact with the ion. The way a substance dissolves is by this continuous process of removing the ions from the solid state and forming these hydration spheres. So eventually, so many ions have been removed that there is no longer a crystal of sodium chloride in this case. It has been completely solvated. Previously, in the first unit, we looked at the different types of solutions that you can form. It can be gas-gas, all the way up to solid liquid. This time, we're going to be looking at which one is the solvent and which one is the solute. So remembering that the solvent is the one that's present in a larger amount, we can say, well, looking at the gas-gas solution, air is 78% nitrogen, so that means that the solvent is going to be nitrogen, and the oxygen is going to be the solute. Looking at the next example, carbonated drinks are made by dissolving carbon dioxide gas in water. Pretty much gives it away. Water is the solvent, and CO2 is the solute. Liquid-liquid solutions, a very common one would be vinegar. Vinegar is actually a fairly dilute solution of acetic acid, so concentrated acetic acid is way more pungent than vinegar is. We say, all right, well, we got 95% water, so that must be the solvent, and then the acetic acid would be the solute. And then the most familiar one is where you have a solid dissolved in a solvent, liquid solvent. And so the example here are sports drinks. like Gatorade, Powerade, etc. And not sponsored. And so we say, all right, well, most of it again is water. Water is often called the universal solvent. So there's our solvent. And then in this case, we have two solutes. We have the sodium chloride and the sugar. And the sodium chloride is the electrolyte that they are always talking about when they are in the commercials. So speaking of electrolytes, we have some definitions. So an electrolyte is a solution that contains ions. Because it contains ions, it can conduct electricity. So here I have a media clip from the Center for Professional and Distance Education at the University of Central Oklahoma, where they're going to illustrate how we can tell the difference between an electrolyte and a non-electrolyte.
The term electrolyte is a term used when talking about solutions with water as the solvent. We'll demonstrate the property of being an electrolyte with an electrical conductivity tester like this. Pure water does not conduct electricity. I will put the electrodes of the apparatus into the beaker of water. There's no light coming from the light bulb. If I dissolve a material in this water and the light lights very brightly, the dissolved material is called a strong electrolyte. As an example, here is a small amount of table salt. I'm going to add just a little bit to the water and stir it up. As it dissolves, the ions of sodium and chlorine, which are charged particles, go into the water, which will now allow the solution to conduct electricity. So the ionic substance, table salt or sodium chloride, is a strong electrolyte. The term non-electrolyte refers to a substance which dissolves in water but does not allow electrical conductivity. Here is some sugar, which I will dissolve in the water.
Notice he's put quite a lot more sugar in there than he did the salt.
As the sugar dissolves, the light does not light up. So sugar is a non-electrolyte.
All right, so we saw the demonstration of the difference between electrolytes and non-electrolytes. Non-electrolytes are typically things that have covalent bonds in them. So things like sugar, hydrocarbons, although they wouldn't dissolve in water. They will not conduct electricity because they don't contain any ions. An exception to this would be things that form acids in solution. They do produce ions, and so they will conduct electricity, even though they have covalent bonds in them. All right, so now we're going to talk about different degrees of how much will dissolve. So a saturated solution is one in which no more solute will dissolve. It's kind of like if you have a big puddle that you're trying to soak up and your rag or your towel or whatever you're using has become totally soaked. It's totally saturated with water, and you can't get any more water to be absorbed into the towel. So same thing for saturated solutions. You can't get any more of the solute to dissolve. An unsaturated solution is one where you haven't hit that saturation point. So if you add more solute to the solution, it will dissolve. And then a supersaturated solution is one, it's actually a metastable solution. It's one where it's very difficult for the solute to form the solid crystals. Sodium acetate is a classic example of this because the acetate anion consists of it's C2H3O2, and it's very flexible. It can rotate, it can bend around, so it's very difficult for the acetate anion to get itself lined up properly to be a crystal. So you can kind of trick that one into having more dissolved than is normally possible. So here is a demonstration of supersaturation. I found this particular media clip in 2006 and have long since lost what the link was for it. There is an alternative media clip available through ChemEdX that shows a similar thing. If anybody knows who this person is, let me know. and I will be happy to credit them. So go ahead and get him started.
Now, this is a very chancy thing to do, because as soon as I pull this cork out, there may be some microscopic crystals in the top that will start the crystallization to go. So I want the camera to come down and show the temperature on this thermometer right now.
Yeah, and I know you can't see the numbers.
Okay, that's good. What's the temperature, folks?
Fluid in the inside of the thermometer.
It's about 25, isn't it? Okay, now I'm going to try to put this in the liquid without any crystallization going on. I don't know that I'm going to be successful. I'm going to pop the cork right now and stick the thermometer in, and we hope the crystals don't start to form. Yeah, right. Thanks for the sound effects. Oh, now look. Now I was successful on that, right? Okay. Now, take a look. Just to show you that the temperature is not elevated.
See the crystals forming.
Come on down and take a peek. Oh, there it goes. Look, the crystals are beginning to form. Now, okay, now come up to where the thermometer is.
All right, so it's right there.
And notice that where the bulb of the thermometer is, the crystals haven't gotten there yet. And suddenly, when the crystals get there, the temperature begins to go up. Right. A good example of crystallization being an exothermic process.
Which kind of makes sense, because you're going from something that's kind of like a liquid state, which is a higher energy state than the solid state that it eventually ends up in. And so that extra energy has to go somewhere, so it gets given off to the surroundings, and the thermometer picks up the change in temperature. All right, so if you are faced with a bunch of solutions and you want to figure out if they are unsaturated, saturated, or supersaturated, there is something called a crystal test that allows you to do so. So what it is you just drop a very small crystal of the solute, and in the case of an unsaturated solution, if the crystal falls in and dissolves, then that was an unsaturated solution. If you drop the crystal into a saturated solution, yeah, it'll break up because of the interactions with the water molecules, but you'll end up with solid sitting in the bottom of the beaker afterwards. And then supersaturated solution, as we just saw, if you get just a little bit of a crystal falling in there, it will form a whole bunch of crystals within the solution. So solubility is the number of grams that you can get of the solute to dissolve in 100 grams of water at different temperatures. And what solubility curves are, they will show the maximum number of grams of a solute that dissolve in this 100 grams. Sometimes you'll see it as 100 milliliters of water, typically, at different temperatures. So what these solubility curves do is they compile mountains of data into a picture that we can just interpret. So we'll go ahead and look at some understanding check questions. So is sodium nitrate or potassium nitrate more soluble, so more grams dissolved in that 100 grams of water at 50 degrees C? So what you do is you go to the temperature and you say, all right, so I want the one that has the greatest number of grams, or the greater number of grams. And so we actually hit potassium nitrate first. So that means that sodium nitrate is the one with the greater solubility, because it can contain more grams dissolved at that particular temperature. And then the next one, so we have a solution of ammonium chloride at 80 degrees C. It wants to know if it's saturated, unsaturated, or supersaturated. So these lines refer to the maximum number of grams. That means if it's on the line, the data point that you're talking about, it is saturated. If it's under the line, it is supersaturated, and I'm using potassium nitrate for some reason. And if it's over the line, it would be supersaturated. So it's talking about ammonium chloride, and our data point is 80 degrees C and 80 grams. So you can see that we are over the line for ammonium chloride, so that means that this would be a supersaturated solution. wants to know which compound is least soluble, so we want to look at the one that is lowest down on the y-axis at 40 degrees C. So we go to 40 degrees. The first one we hit, the one with the lowest solubility, is cerium sulfate. So we're back at that 80 and 80 point, but this time we're talking about potassium nitrate. So you can see we are still under the line for potassium nitrate, which goes all the way up like that. So that particular data point would be unsaturated. And then the last understanding check question, this is the one that seems to give people the most trouble, is talking about what temperature will crystals appear for the solution in number 4. So thinking back to those crystal tests, the only point at which you can get crystals is when you have, the earliest point you can get crystals is when you have a saturated solution. If you drop one little test crystal in there, it doesn't dissolve, it just falls to the bottom. So we are stuck with the 80 grams of potassium nitrate. So we're going to cool it off. So we're moving along horizontally along the x-axis. And then we hit the saturation point for potassium nitrate, our solute, at 50 degrees C. So 50 degrees is going to be the earliest, the warmest temperature that you will be able to first begin to see crystals forming. All right, so that is it for solutions and solubility. Thanks for listening.